Okay, welcome everybody, and we have Dr. Pieter Kotzé talking about mysterious magnetic fields of the solar system. The description which Peter sent out on email to everybody looked quite intriguing, so I'm looking forward to this, as I'm sure are you. So can you please all just mute your mics while Peter is talking, in case dogs bark in your background or something. And then if you want to ask a question while he's talking, you're welcome. Otherwise, just ask afterwards in the question session. All right, thanks very much. You can go for it, Peter.
Thank you, Derek. Good evening, everybody. As we know, we live in a universe where magnetic fields can actually be found in every corner of the system. Our own solar system is no exception, actually. And tonight I would like to share with you some of the mysteries around magnetic fields in our solar system, where we actually can find all shapes and sizes of magnetic fields you can ever imagine. So to start off with, the majority of our planets in our solar system do have magnetic fields. However, magnetic fields can actually disappear, as what happened on Mars, and some planets do not have a magnetic field. As a matter of fact, as an interesting fact, there's only one moon that we know of at the moment in our solar system that has an internal magnetic field. However, with the knowledge at our disposal at the moment, magnetic fields can change orientation, they can even reverse polarity, and as such, planetary magnetic fields can change with time, and that feasibility or characteristic actually can provide us with a view of internal processes taking place in a particular star or even in a planet. So tonight, I would like to introduce to you our tour guide. I call him Mr. Compass Astronaut, who will travel with us through the solar system. And wherever we make a pit stop, he will start introducing us to whatever can be seen on his compass at a particular moment in time. So let me start off with our own sun. The sun has a very strong magnetic field. Actually, it's the strongest magnetic field in our solar system. The magnetic field can change polarity. In fact, every 11 years during the period of a solar maximum or the maximum activity of a solar cycle, the magnetic field changes at the poles. As we can see here, it's a positive magnetic field in this area between 75 and 1980. And then where the green arrow is, it changes polarity. And then another 11 years, it changes polarity from negative to positive, and the same happens here in the southern hemisphere. Also, in addition to that, during a solar cycle, the magnetic field changes from higher latitudes to lower latitudes, decreasing and then going through a period of zero, and then increasing again for the next solar cycle. So these reversals are actually a key feature of the solar dynamo. That is basically the physical process that generates the sun's magnetic field necessary for the creation of sunspots, coronal holes, and coronal mass ejections. And we can see here progression of sunspots during the last two solar cycles. So the solar magnetic field polarity reversal has a profound influence on one particular property in our universe, and that is the modulation of high energy galactic cosmic particles in the heliosphere. Tonight, I'm not going to concentrate too much on that. I'm just going to skip over and show you what happens to magnetic fields as we travel along. So one of the big mysteries that puzzled astrophysicists for a very long time is, why is the sun's corona actually so much hotter than the surface of the sun? On the surface, we found the temperature around about 6,000 degrees. Further out in the solar corona, that is the sun's atmosphere, the temperature rises to a few million degrees. And the latest information and data that we can gather from the Parker Solar Probe actually shows us that there is an explanation for that, and that is the reconnection of magnetic fields in the sun's solar corona. This reconnection or changing of polarities inside the corona leads to the creation or the conversion of stored magnetic energy inside the corona, converting it to heat and kinetic energy, and then energizes particles streaming out from a coronal hole, for instance, and then also heating up the sun's corona in the process. So magnetic reconnection is a process that not only takes place in the sun's atmosphere, but it is also crucial in the Earth's magnetosphere, where it is responsible for magnetic substorms and magnetic storms, creating or converting magnetic energy into kinetic energy and giving rise to the well-known auroras that we see from time to time. And especially this time of the year is the famous for the coronas to be seen, or auroras, and then that is the time when we near equinox, and that is the geometry is actually quite favorable to observe these aurora effects this time of the year. So our next stop, that is Mercury, the closest planet to the sun. It still has a liquid iron-rich core and has a magnetic field that's approximately 1% as strong as that of the Earth. The orientation of the magnetic field is close to similar to that of the Earth, with the north magnetic field, a pole in the southern hemisphere, and the south magnetic pole in the northern hemisphere, leading to the curving of magnetic field lines coming out in the solar hemisphere and entering into the northern hemisphere. However, because the Mercury is so close to the sun, it experiences quite an amount of solar wind interaction, almost 7 times stronger than the solar wind here on Earth. So with a core that outputs a magnetic field only 1% of that of the Earth and a strong solar wind battle against it, Mercury is only capable of maintaining a very tiny magnetosphere. That is the magnetic bubble around the planet. It's actually so small that it can actually fit right inside the Earth. At the moment, as we speak, there's a satellite called Bepi Colombo. It's a joint mission between the European Space Agency and JAXA, the Japanese space agency. It's currently en route to Mercury and will arrive at the planet around about 2025 to make a thorough investigation of the magnetic field and other surface properties of this particular planet. However, Messenger was another satellite that operated between 2011 and 2015, and it gathered very interesting magnetic field data from Mercury. One feature that I would like to highlight is the magnetic data from a crater or an impact crater called Rustaveli. And as we can see in this view graph, the magnetic field inside the crater is completely different to the magnetic field outside the crater. To make a long story short, when the asteroid impacts onto a planet, creating an impact crater, it heats up the mantle or the rocks inside, completely demagnetized it, and then as it starts cooling down, the magnetic field or the rocks get remagnetized, and they take on the magnetic field that is prevailing at that moment in time. So what this indicates to us is that the magnetic field a very long time ago, a few million years ago, was completely different to what it is actually at the moment. What is also interesting about that, the findings in this crater, is that the geographic north and south poles are completely different today than it was when the ancient magnetic field in Mercury actually prevailed. So that indicates to us that polar wander is actually taking place on a tiny planet like Mercury. So the magnetic poles can actually wander around, similar to what is currently happening on Earth itself. The Mercury magnetic field is between 3.7 and 3.9 billion years old. As I said, it's about 1% of the Earth's magnetic field. It also found from the messenger's observations that it's shown a very weak secular variation. That is the variation in time with the Mercury's magnetic field. So Mercury has a very peculiar characteristic that it can change with time, similar to what we actually see on planet Earth. So in addition to that, Mercury's magnetic field is dipolar. That is, there's a clearly defined north and south pole, which is actually strongly asymmetric with respect to the equator. Now that means that the field of magnetic field strength in the northern hemisphere is approximately 3 times stronger than the magnetic field in the southern hemisphere. Now that indicates to us that there is an asymmetric heat flux in the interior of the planet. Why it is taking place, we don't know. We hope Pepe Colombo might share or put some new light in that regard, but at the moment we don't know. That is only the indication on the surface that the heat generating dynamo interaction inside the core of Mercury is completely asymmetric. In addition to that, the magnetometer measurements from MESSENGER also showed that the magnetic equator is displaced on Mercury in a northward direction, which indicates to us that not only is there a dipolar magnetic field present on Mercury, but it has also got a very strong quadrupole component. That is the 4-pole component that we also see on planet Earth. So the next stop of our tour guide is at Venus. Venus is a very strange planet, as you all probably know. It's the only planet in the solar system that has got no internal magnetic field. And we think at the moment that it is due to its very slow rotation period of 243 days. It is the only planet in the solar system that rotates slower around its axis of rotation than it takes for one orbit around the sun. At the moment, we know that the orbit takes about 225 days for Venus to complete an orbit. And in addition to that, Venus is also the only planet that rotates from east to west, completely opposite to the other planets that rotates from west to east. So due to the lack of an internal thermal convection, we think that the liquid metallic core is rotating too slowly to generate a measurable global magnetic field. However, when Venus has got a very dense atmosphere, and with the solar ultraviolet radiation from the sun, it's very easy to ionize the atoms inside the atmosphere and create an ionosphere similar like we have here on planet Earth. So when the solar wind interacts with the ionosphere or the atmosphere of Venus, it carries with it the sun's magnetic field. So the long and the short is, Venus is able to form an induced a magnetosphere without an internal magnetic field. So that is one of the peculiarities of this particular planet. It seems like it has got an external magnetic field without any internal magnetic field present. Now we come to a very interesting scenario with the Earth and the Moon. At the moment, according to recent published research, it shows to us that the Moon was formed around about 4.5 billion years ago, when a Mars-sized object called Theia actually slammed into the proto-Earth when our planet was less than 100 million years old. So that the process led to the forming of a magnetic field on the Moon itself. So the Moon and the Earth at one stage in their lives shared a common magnetic field or magnetic field lines, because at that moment, 4 billion years ago, the Moon was almost 3 times closer to the Earth than it is today, approximately 128,000 kilometers in comparison to the current 380 kilometers. So in this illustration, it shows that both the Earth and the Moon had magnetic fields that were connected approximately 4.1 to 3.5 billion years ago. And that helped to protect the atmospheres from streams of damaging solar particles, according to a publication that appeared some time ago. So how do we know that Moon had a magnetic field? Analysis of basaltic rocks brought back by the Apollo astronauts concluded that the Moon must have had a magnetic field sometime in its past and in its history, approximately 3.5 billion years ago. And only the rock samples, and some rock samples actually did not show any magnetic field. So it indicates to us that some process took place on the Moon, cooling down the internal core that it must have had at one stage, and leading to the disappearance of its own magnetic field. So only the rocks on the surface, what we call crustal magnetic fields, are still present on the Moon itself. The Earth, that's our next stop for our tour guide, is the Earth. We all know the Earth has got a very important magnetic field that plays a crucial role in our lives, protecting our atmosphere and also prevent life from being extinguished by the harmful radiation from cosmic energetic particles. The Earth has got
sorry, Derek, can I just ask a quick question?
Yes.
Just on your presentation here, you've got the sort of main slide and then the next slide displayed next to it and some text underneath. Is it possible to just display the main slide so it's a bit bigger? I see there's a display settings on the top there in the middle, in the menu on the top in the middle. Maybe.
Okay, yes.
But I don't know if you prefer it like it is now or no. No, that's not it. No, maybe oh wait, at the bottom here there's like a full screen thing. Well, maybe one of those. Swap it to maybe the third one. It shows the computer there. No, that just blanks it off. Okay.
Yes.
I don't know. Okay, just carry on. Sorry, we're wasting time.
Okay, yes. So the Earth has got an internal structure with a solid inner core surrounded by a liquid metallic core, and that is where the Earth's magnetic field is being generated, and leading to the north magnetic pole in the southern hemisphere and the south magnetic pole in the northern hemisphere. But in addition to that, we also know that the poles are wandering at the moment in time. The north magnetic pole traveling approximately 50 kilometers per year from North America in direction of Siberia, and with Mr. Putin having all smiles and licking his lips to entertain the arrival of the North Magnetic Pole in his domain. But in addition to that, we also know that the Earth's magnetic field has got anomalous structures like the South Magnetic Anomaly, which is at the moment splitting into two different sections, one closer to Africa and one centered around, across the South America. And that we believe and we think at the moment is the forerunner of a magnetic field polarity reversal. In this little slide animation video, I'm going to show you what happens during a polar reversal. The Earth's magnetic field going through a very low period, the dipole field, and then several north and south poles appear on the surface of the Earth, leading to the quadrupolar structure of the Earth to dominate. So that is something that happened in the past on several occasions, as is shown here in this diagram. At the moment, we are in the blue section. That the last polarity reversal took place 780,000 years. So on a statistical basis, we are actually overdue for a magnetic polar reversal. But that is a story for another day. And I think there's a presentation coming up later this year to explain the appearance of certain magnetic phenomena on the Earth itself. So the magnetic field changes with time, and particularly very strongly during a magnetic storm. And what I'm going to play to you now is when you convert the variations in the magnetic field to sound, and that is how it sounds a magnetic storm on the 3rd of November of 2011. I'm not going to play you the whole thing. It's just to give you an indication of what can happen during a magnetic storm when you convert the signals to a sound system. So Mars is the next stop from us out to the outer stages of the solar system. We now know that Mars once must have had a magnetic field. And how do we know that? There is an impact basin called Hellas. It's in the southern highlands of Mars and is one of the solar system's largest impact basins. In fact, it's approximately 2,300 kilometers in diameter and a depth of approximately 7 kilometers. Hellas is thought to have been formed between 3.8 and 4.1 billion years ago, when an asteroid with a diameter of approximately 100 kilometers hit the surface of Mars. So what we see on Mars is that the Hellas Basin has got no magnetic field, whereas there are strong crustal magnetic fields surrounding it. So why is that so? We think that when the impact took place and it demagnetized the rocks in this area, there was no magnetic field again to remagnetize the rocks in that area. So it stayed dormant and there's no magnetic field present. So that indicates to us that Mars must have had a very strong magnetic field similar to the Earth in its early lifetime, soon after it was formed actually. If you compare the crustal magnetic fields at an altitude of 400 kilometers on Earth, we see that it ranges between approximately 20 nanotesla negative to 20 nanotesla positive. On Mars, however, at the same altitude, it ranges almost 10 times stronger. So that indicates to us that the magnetic field on Mars must have been massive when it actually existed. So for Jupiter, on the other hand, Jupiter is the strongest, has got the strongest magnetic field of all planets. And it's much more complex than the Earth because the gas giant has a very rapid rotation rate, approximately 9 days or approximately 9.9 or 10 days for one complete rotation around its axis. The North Magnetic Pole is in the northern hemisphere, the South Magnetic Pole is in the southern hemisphere. But in addition to that, Jupiter has got not only got one North Pole, but it has got two South Poles. And that became clear from results obtained from the Juno mission that is currently flying around Jupiter. It made the first definitive detection beyond our world of an internal magnetic field that changes over time. That is one feature that is not common throughout the solar system, and Jupiter shares that with the Earth. So that is what we call a secular variation. So Juno determined that the gas giant's secular variation must, in all probability, most likely be driven by the planet's deep atmospheric wind. So we also, results indicate that the secular variation is the largest around the blue, what we call the great blue spot in the southern hemisphere, which is very most intense magnetic field near Jupiter's equator. In addition to all planets that has got a magnetic field, has also got global so-called what we call radiation belts. And one of the moons of Jupiter is Io. It's the most intense volcanic active system in our solar system with close to 400 active volcanoes. So it's spewing out oxygen and particularly sulfur dioxide and also sulfur into the magnetic field, interacting with the magnetic field of Jupiter, flying into the north and south poles of Jupiter. And at the moment, we are capable of seeing the most intense aurora displays in our solar system on the planet called, on planet Jupiter. So that indicates to us is another feature that is a result of the very strong and intense magnetic field of this particular planet. It's not only the sulfur ions and other atmosphere or atoms that are released from Jupiter, is also the electrons from Io are also accelerated by the planet's massive magnetic field. Jupiter has an enormous, as I said, it rotates very rapidly around its axis of approximately 10 hours. Those two characteristics mean that the planet's magnetic field actually acts as a giant particle accelerator. And it is capable of, with latest detections from the NASA's Nuclear Spectroscopic Telescope Array, in short, New STAR, it's a space observatory, it's able to detect the highest energy light ever detected from any planet in the solar system. It's called the X-rays that we can detect. So as a result of that, by studying Jupiter, researchers are now able to not only study Jupiter, but also details of distant sources that cannot be visited, like white dwarfs or magnetars or whatever. So that serves as a laboratory for studying systems that are not easily accessible for our current technology. As mentioned in the introduction, that is one moon in the solar system that has got an internal magnetic field, and that is Ganymede. It's slightly larger than Mercury, approximately 8% larger than Mercury. It's approximately 2/3 the size of Mars and a diameter of approximately 5,300 kilometers. So the Galileo spacecraft in 1996 actually detected the magnetic field that, and in addition to that, observed auroras on this moon that is not possible on any other moon in our solar system. We think that the magnetic field is most probably created by convection within its liquid iron core, which is kept in a liquid form by the tidal forces acting from the Jupiter's very strong magnetic field. So Ganymede is the largest, not only the largest moon in the solar system, much larger than planet Mercury, and if it had not been orbiting the Jupiter's largest moon, it could have been considered a dwarf planet. So if we turn our attention to Saturn, Saturn has got a magnetic field in the opposite direction of the Earth, but it is almost perfectly symmetrical around its rotation axis. We think that Saturn has got a rocky internal core surrounded by metallic hydrogen, and then it is, in addition to that, there's a layer of helium insoluble mixture further out towards the edge of Saturn, and then there's molecular hydrogen. All these constituents creates the environment for a dynamo action to create a magnetic field in this particular planet. Uranus, on the other hand, where we next make our stop on our tour, is the only planet whose equator is nearly at a right angle to its orbit. It's almost lying flat on its back, and it is most probably the result of a collision with an Earth-sized object in its early lifetime, soon after it was actually formed in the solar system. But in addition to that, Uranus has got the weirdest magnetic field in the solar system. The magnetic poles of Uranus are not at all close to the geographic poles of the Uranus. The magnetic field actually is actually tilted 59 degrees away from the planet's spin axis. Added to that is the fact that Uranus rotates on its side as it circles the sun. So we think that Uranus has a magnetic field that is generated by convection currents in an electrically conducting interior and was first discovered by Voyager in the late 1980s, early 90s. So in some places in the southern hemisphere of Uranus, the magnetic field is approximately a third of as strong as the Earth's magnetic field. However, in some parts in the north, the magnetic field is actually 4 times as strong as that of the Earth. So a highly asymmetric magnetic field, a very strange rotation periodicity, and generation of a magnetic field that is actually completely awkward to what we normally observe on our inner planets of the solar system. Neptune was also detected. Our next stop is first detected in 1989 by the Voyager 2. It's also tilted 47 degrees from the planet's rotation axis. And the dynamo electric currents produced within the planet are much closer to the surface than Earth, for instance, or Jupiter or Saturn. The magnetic field is approximately 27 times more powerful than the Earth. It sits at an angle on the planet and is changing chaotically as it interacts with the solar wind. So like Uranus, the magnetic field is radically different to that of what we are seeing on Earth. It's not only, it's not aligned with the rotation axis, of Neptune, but is also located, not located at the center of the planet. So it's off-center. So the best theory at the moment for the origin of these magnetic fields is the presence of a high concentration of soluble ammonia, which is highly conductive in the planet's interior, and that is most probably giving rise to a dynamo action, leading us to the creation of a magnetic field in Neptune. So to summarize, among the 8 solar system planets, we see that 6 have large-scale intrinsic magnetic fields. These large-scale magnetic fields can be classified into 3 groups in terms of their morphology. The first group is actually dominant, is dipolar, equatorial is symmetric, like Earth, Jupiter, Saturn. Then we get the second group that is non-axial. That includes the fields of Uranus and Neptune. Then last but not least, the third group is the actually dominant magnetic field. It's predominantly dipolar, but equatorially asymmetric. That is what we can normally find in a planet like Mercury. So Earth's magnetic field has got a very particular characteristic that it changes with time on time scales roughly between 2 to 3 years. It can even reverse its poles. And in addition to that, Jupiter shows the only other planet that shows a very slow time variation. So on this score, thank you very much for listening. And this is to cap off what can happen when you fall out of your bed at night and start blaming the Earth's magnetic field for that. Thank you very much.
Thanks very much, Pieter. That was fascinating. I learned a whole lot of stuff, a lot to take in there. A quick hour, almost an hour. Have we got any questions there for Pieter?
Yes, Pieter, thank you very much for an interesting talk. I thought that, and it seems that my intuition was correct, that the vanishing of Mars's magnetic field was linked to it, the freezing up of its core. And you did always say that where you find the magnetic field, it is always associated with a rotating liquid core. So is that conclusion correct?
That's absolutely right. Otherwise, you cannot generate a dynamo. You need a conducting liquid inner core that rotates at a certain critical speed in order to generate a magnetic field. So that is what happened on Mars. It had a magnetic field, and we suspect that the internal core actually cooled down to a critical level that it couldn't sustain its own magnetic field, and therefore the protective shield for Mars atmosphere actually disappeared, and that is the outcome that we see today with this almost desert-like environment on Mars with no sign of any life or forms of life at the moment, although there's a huge amount of effort going on to detect whether Mars had entertained primitive or microbial life in the past, but we know that Mars had water on it and flowing water. We could also see from the Hellas basin that there were signs of water and liquid water that once flowed on the surface of Mars.
Thank you, Pieter. So the same happened to the moon. How long is Mercury going to last with its magnetic field?
That is an open question. I think these answers will be answered, or questions will be answered by the next satellite mission currently on its way to Mercury. That is the Bepi-Colombo system. Messenger gave us a little peep into what is currently happening on Mercury, but we cannot say for sure what is actually the real situation. My personal suspicion is that the sun's interaction with the liquid core of Mercury is sustaining it long enough, or might sustain it long enough to generate a magnetic field for quite a substantial amount of time in the future.
Thanks, Pieter.
Pieter, the soundtrack you played of that, was it the magnetic field? The sound of a magnetic field, just remind me?
Yes, they took the variations of the magnetic field as recorded by a magnetometer and then converted it to sound. And that is what they provide. I can send anybody who's interested in it the sound clip, and then they can play it at leisure at home. It's much longer than I played it, but it's just to illustrate you that you can convert magnetic field variations into sound, and then gives you an idea of what happens, or how, or what timescales a magnetic storm actually prevails in the Earth's magnetic field or magnetosphere.
Yeah, it sounded like a whole lot of stones rattling against a window. It's quite impressive.
Yeah, almost like a fire crackling in the background.
The period when the moon was so much closer to Earth would have meant a lot more eclipses and more total. Would that in any way have affected the earlier days of Earth, having a lot more eclipses?
I would suspect so, and I would also think that the effect of tidals would also have been much stronger than it is today. So it might have been a very fascinating time, but in addition to that, it's also very in the early stages of the Earth's development, about 100 million years into its own, after it was only formed. So we don't know what was on the surface of the Earth at that stage. But if there had been water, I think it might have been quite a substantial amount of high tides and low tides. So that is one thing that I can think of immediately, what could have been the effect of a very close moon to the Earth itself.
Thank you.
Pieter, sorry to ask another question. You said nothing about Pluto. Were there no measurements from the voyages or from New Horizons, magnetic measurements?
There was no indication of any magnetic field on Pluto at all. So we don't, at the moment, there's nothing to indicate that Pluto had a magnetic field or might have had one in the past. So Pluto is completely devoid of any magnetic field. I suspect also Ceres might also not have a magnetic field, but one never knows. It could be, if you can't detect aurora on the planet or on a moon, that is the first sign that there's no magnetic field around it. So, and that is what we can actually see on Ganymede, that there are signs of aurora activity on that moon, and that was the first suspicion that that particular moon had an internal magnetic field.
Pieter, I would just, sorry, can I ask a quick question? I was just looking at on Sky Safari, the description of Jupiter's magnetic field, and it says that, I don't know, I think you mentioned it's more than 1,000 times stronger than Earth. But the magnetic bubble around Jupiter is so enormous, according to this description, it stretches out beyond Saturn.
Yes,
so it must interact with Saturn. I mean, there must be any sort of visible interactions that are recorded there by satellites.
Yes, I think so. That is a true fact. And the magnetic bubble stretches actually 5 astronomical units away from Jupiter. So it's unreal, and it's massive, so to speak.
I see the Sykes have a polite hand in the air, so maybe they need a question.
Yeah, go ahead.
Yeah, sorry, it's me. And I was just wondering how this fluctuating or varying magnetic field on Earth, and what effect does it have on our everyday life, on navigation, etc., and how, if you could just speak to that a little bit.
Yes, fluctuating magnetic field, particularly during magnetic storms, can play havoc with any navigation system, particularly a compass, but also with your GPS system, because when your ionosphere is disturbed due to a magnetic storm, the path from the satellite to your detection system or your receiver in your motor car is also affected. And that can lead to erroneous measurements, particularly when you need very fine navigation applications. For instance, when they drill for oil, that needs to be very highly precise. Also for navigation of projectiles, like they now use in various parts of the world to destroy infrastructure during wartime, that needs to be guided very, very precisely with a GPS and taking into account fluctuations in the Earth's magnetic field. So those things can lead to very profound side effects for humankind, apart from the blackouts that you experience in shortwave radio communication. That is a very dangerous effect that can take place for pilots, particularly when they fly during magnetic storms. They need to take cognizance of the fact that they might not have shortwave radio communication, and then they need to revert to other flight paths, particularly over the polar region, and that costs money. In addition to that, one of the laws of physics is when you have a fluctuating magnetic field, you also induce an electric current. And that current takes the nicest and shortest route it can detect at that time, and power line systems is also vulnerable to these direct current. You know, a transformer or a power line is designed for alternating current and not DC current. So it happened in the past in Ruacana, I think that was during a storm of 2003, that one of the transformers actually burnt itself to pieces. It heated itself, the oil heated up, and then the transformer was destroyed. A similar thing happened in Quebec in 1989 during that famous storm. That's also during a March period. As I mentioned, that is a very strong period for magnetic storms. The whole of Quebec was blacked out for several hours, and the people didn't know what to do at that stage. It was quite new to them. So even garage doors, well, the emergency police were driving up and down, trying to make contact with their own systems or their own head offices. They were tuning into radio frequencies that actually interfered with the automatic door openers of the people, and the garage doors were actually flipping up and down all the time due to people switching the frequencies around. So there are many things that I can think of that can happen and make your life completely miserable. Apart from load shedding that we currently have with no power, it can also happen that the system can be knocked out completely, and then you have a worst case scenario like a day zero. That was happened in Quebec. So in short, yes, fluctuating magnetic fields during a magnetic storm is not something that you should look forward to in all due respect. I hope that
and how would we detect in daily life that 2 to 3 year variation you spoke about as the wandering of the...
No, that is the secular variation. That is only for navigation purposes. You need your declination maps to be highly accurate in a certain area, particularly Southern Africa, with these fast-changing magnetic fields that even changes on times or timescales shorter than 2 to 3 years. Even in a period of 1 year, you can see quite a substantial change in your magnetic compass deviation. So that is very crucial, or is actually a crucial fact, to update that and with the latest information available for navigation purposes. So that is something that SANZA is doing on a regular basis. That is what the old magnetic observatory was responsible for, and they are still one of the major activities is to look at the magnetic field changing, particularly with the presence of the South Atlantic magnetic anomaly actually on our doorstep. That is something that is crucial, and it needs to be regularly updated, particularly for people relying on magnetic navigation, because that is by law, every aeroplane and boat in this country is required to have a magnetic compass on standby, but you never know when your electrical system can be knocked out inside your vehicle or your boat or aeroplane of any kind whatsoever.
Pieter, I think a question that also comes up quite often is with that long-term total polar reversal. Are there any sort of mass extinctions that have happened at those times in the past, or even partial extinctions? And when, I mean, the next one is overdue, but has anybody got any idea? Is it going to be in 10,000 years? Is it going to be in 10 years? And what will the effect of a polar reversal be on Earth and Earth's life at that time? I mean, will the sun sort of be much more dangerous and this sort of thing, radiation and stuff?
Yes, what happens during a polar reversal, your magnetic field will not drop to very low levels. Actually, the estimate is that approximately 10% of the current magnetic field will prevail during a polar reversal. And the polar reversal does not take place overnight, or it takes several thousand years to actually complete. So during that time, as I said, you will observe more than one north and south pole appearing on the surface of the Earth itself. So for migrating animals like whales and pigeons, that sort of thing, they will be in for a very rough time. But in short, we could never detect any form of mass extinctions during polar reversals in the past. So I don't think it will be that dangerous, but we must also take into account what at the moment, we are living in a very highly technologically advanced society that we never know what the effect will be. The estimate is that skin cancer induced or radiation skin cancers will increase quite dramatically, approximately 100,000 more per year, but that does not define a mass extinction. So we might see people more vulnerable to radiation damage because there's less screening of energetic particles from outer space, but not to the extent that we might see people dying or intelligent life being wiped out from the planet itself. So I personally think we won't be too much in for a rough ride, but we must be careful, particularly for navigation purposes, that we must need to take precautionary measures. So I think the estimate is that the next polar reversal, if the tendency of these anomalous magnetic flux patches appear on the surface of the Earth, that the next reversal will start taking place in the next millennium. But in the past, there was also false excursions where all the signs took, as we can get from geological record, that there were signs of a polar reversal trying to take place, but then the magnetic field flipped back again to its normal or original orientation. So that can also happen. And at the moment, we don't really know for sure. We cannot place a date on it. We cannot place a time on it. But that is something that in all most probability will happen in the future again, as we can see from our record of polar reversals in the past. I hope that answers more or less a question.
Well, that's very comprehensive. Thanks, Pieter.
Yeah. If it limits itself to Earth mainly, the fact that we've got more and more satellites going out into deeper space, is there some possibility that an alternative to magnetism might take over some of the technological basis that could enable advancement to continue without being so dependent on magnetic fields?
I doubt it. I think magnetic fields will be with us, and magnetic field-based technology will still be with us. That is the most or available or technology to us. I'm not aware of any developments to replace a magnetic field-based technology. The main advantage of the magnetic field of the Earth is nobody can take it away and exchange it for money at a pawn shop. So for that matter of fact, we are still fairly safe. And I think at the moment, people are developing technologies taking into account or assuming that we will have magnetic technology available to us for quite a substantial amount of time. Although we might have GPS-based navigation systems that can fail. It happened in the past. I can name numerous effects that took place in the wars in Afghanistan when there was a magnetic cloud or perturbation. The people couldn't make contact with a combat helicopter, and the Taliban actually had to feast in shooting down the helicopter that couldn't avoid a certain area due to the lack of communication via GPS and also shortwave radio communication. So that's just a simple example of what can happen when you when you are exposed to magnetic fields with perturbations in the Earth's atmosphere.
Thank you.
Yeah. Could I just ask another question? You know, these missions go into outer space and look at the planets. If they encounter some of these very strange magnetic fields, does it interact with the spacecraft's you know, with the navigation service, and do they then have to make alterations or change it or allow for it?
No, I can only think of the 2 Voyager missions that are now actually outside our solar system. The magnetic fields are so weak in that area that they has no effect whatsoever on the navigation or the communication systems of that particular satellites. But we also take into account that the technology on those satellites are actually ancient and does not exist anymore on Earth. Like, for instance, tape recording. They have like these tapes running backwards and forwards for recording of data and scientific measurements, and it has never failed. So at the moment, fingers crossed, nothing has happened so far that warrant any drastic interaction from Earth to make any drastic changes in terms of uploading signals or new data to the satellites to change that. It has never been very close to any other heavenly bodies or planets or stars or whatever you can call it. So I think at the moment it's honky-donkey and it's going fairly well in terms of that. So there's no hiccups at the moment for those two satellites. That is the ones that I can think of most probably that could have been affected by external strange magnetic fields. Similar to the New Horizons that's now traveling in the Oort and deep into outer space, and it has never encountered any serious problems in that regard.
I think the knowledge of our membership is humbling. Thank you.
Any more questions for Pieter? I think that was very, very fascinating. Thanks very much, Pieter. Go ahead. Was that you, Pieter? Okay,
yes, that's me. And just thanks. That was a real pleasure.
Fascinating. Okay, no more questions. Last chance. All right, then we'll say thanks to everybody and thank you for attending. I hope you enjoyed it as much as I did. And thanks, Pieter. And I'll stop the recording now and then upload it to YouTube. Thanks very much.
Really informative. Thank you. I enjoyed that.
Thanks, Pieter. Good night to everyone.
Okay, thank